Good day, students. Here, let me discuss to you the simplified block diagram for the bathtub water level control system. This is the one that is similar to what you have submitted. So let us recall the problem. Your bathtub at home is a control system that keeps the water level constant. A constant flow from the top yields a constant water level because the flow rate through the drain increases as the water level increases and decreases as the water level decreases. After equilibrium has been reached, the level can be controlled by controlling the input flow rate. A low input flow rate yields a lower level, while a higher input flow rate yields a higher level. We're going to sketch a schematic of control system that uses this principle to precisely control the water level in a tub. Show the intake and drain valves, the tub, any sensors and transducers, and the interconnection of all components. So you're going to draw the functional block diagram of the system, identifying the input and output signals of each block. So this will be the schematic diagram for this water level control. So we have here our bathtub for our process, okay, and it has a water. So to sense the level of the water, we have this kind of float sensor. So this float sensor is a proportional type. This is the float part, wherein if the water level is low, it goes down to where the level is, and as the water level goes up, this float goes up as well, where the water level is. Now, the limitation of this type of float switch is in the length, its length or the height. Okay. So if, for example, literally in this drawing, the height is only this much, okay, as compared to the height of the bathtub, it means that the maximum height of the water will be only at this point. So it's very important to know the specification of your float switch and the specification or dimensions of your bathtub. And then we have here a potentiometer wherein you're going to input here the settings of the water level. Of course, the potentiometer is continuously has a continuous adjustment. Okay, so as you adjust this potentiometer, the resistance of the potentiometer changes, and the current provided as input to this differential amplifier will vary according to the resistance setting of this potentiometer, in which that resistance level has a calibrated level of water into it. Yung bang habang pinipihit mo yung potentiometer, no, may mga scale doon kung to how much degree yung inikot mo, ganung certain water level ang mapupuntahan. So this float, I hope I have mentioned that this is a proportional type of float switch as well, kasi may mga on-off type ng float switch, no? Pag on-off, meaning to say there are only two level of the float switch, the off position and the on position. Usually the off position is the empty level, and the high position or on position is the maximum water level. But for this one, this is proportional type, wherein for every level or position of this float, no, habang tumatakbo yan siya, kung ano man yung actual level niya, ay may corresponding current din, no? So, proportional also. So, as long as there is a difference in current, at the same time, the voltage, no, coming into this input of the differential amp, no, as long as hindi equal, okay, so there will be a voltage output which is amplified. Okay, so ibig sabihin, kunwari, the voltage here is 3 volts, while the voltage here is 1 volt or millivolts, no? That's say 3 millivolts here and 1 millivolts here, so a difference of 2 millivolts, that will be amplified. Okay, so the 2 millivolts difference will be amplified, say, let's say a gain of 1,000 gain. So the 2 millivolts times 1,000 will be 2 volts, no? At sabihin natin, for example, that 2 volts is enough to drive this proportional valve actuator. Note that the setting of the potentiometer is continuous. The current as well as the voltage provided by this float switch is also continuous. So the difference is also a continuous value. So meaning from 2 millivolts difference, it could vary from 1.1 millivolts, 1.2 millivolts, 1.3 millivolts, and so on until it reaches to millivolts, which is amplified in 2 volts. So meaning to say, the voltage coming into this proportional actuator valve is also continuous, and that value, that continuous value will be proportional to the percent opening of the valve. So sabihin natin, if the difference is 1 volt, it's only 20% open ang valve, so mahina lang ang flow rate nun. Pag sinabi nating 2 volts na yung difference na being driven to this valve, so the valve will open for sabihin natin 80% open. So dahil malaki ang opening ng valve, so mas malaki ang inlet water flow rate. Okay? Now, of course, this opening here is from the water supply, from the tap water. No? Okay, and so I believe we understand from the problem that as water is provided, supplied to the tub, so the water level here continuously goes up. And at the same time, there is no drain valve here. So meaning to say, the water is continuously drains out as well. But it's stated in the problem that this process, the diameter of the drain pipe and the diameter of this supply pipe should be designed to be the same, no, equal diameter, no, so such that there would be constant flow of water from the inlet to the tub to the outlet. Okay, if that constant flow between these two will be equal if only they have the same flow rate already. But kailan nga ba mangyayari yon na nag-equal yung flow rate nilang dalawa? Because at start, we cannot say that na-equal agad sila. Okay? So, let's start our assumption na at start, mahina, no? Mahina ang flow rate dito. Kunwari, nasa 20% open lang itong valve. So, syempre, mahina ang flow rate nun. Dahil mahina ang flow rate nun compared sa flow rate nitong outlet, meaning to say, I was saying, to continue, that the the point where the flow rate from the inlet water and the flow rate to the output water will be equal. It doesn't occur automatically. And the very first consideration that we have to think about is when the inlet water flow rate is less than the outlet water flow rate, which means there should be a minimum design requirement, no? That the uh, pipes for the inlet pipes should provide a flow rate that would never less than the outlet flow rate, no? So it has something to do with the diameter of the drain pipe, because this drain pipe is fixed, no? The diameter is fixed, and the inlet is also fixed, but we can control the flow rate by varying the percent opening of this valve. Okay, but the flow rate here is fixed because the diameter is fixed. So I have a note here that in this simple design, the disturbances due to changes in the supply water pressure cannot be uh, corrected. Okay, from the top water, no, the top supply water pressure, it cannot be corrected. So from our previous discussion, from our previous video, that it's a disturbance. Now, if there is a too much low pressure of the top water, we might not achieve equilibrium in the inlet and outlet flow rates, while too high pressure from the top water might overflow the tub. And also, it is important to note that inlet and outlet pipes diameter should be the same, no? At least the same. Okay? So, once more, the very important thing to consider, uh, because the uh, outlet flow rate is not controllable. Okay? So, the design of its diameter should be considered such that the minimum flow rate that can be provided for the inlet will never be below, no, the flow rate of the outlet, or else the palagi na lang yun na nagdi-drain, no? Kung mabilis ang flow rate sa pag-drain, mabagal yung inlet, palagi na lang nagdi-drain yun. Okay, so those are design considerations na kailangan natin isipin, na yun ang limitation dito sa simplified na block diagram na ito. Okay? Unlike doon sa the first design that I've provided you, all those disturbances or limitations are controllable. Okay? Take note also that the summing junction, no, this summing junction, there is no physical device in the actual schematic, no. In this block diagram, it is provided just to show a representation that output water level into the tub is affected by the inlet and outlet flow rates, no? Just to represent, no? So if we imagine the schematic diagram, the actuator valve, of course, it provides water. The amount of water it provides depends on the amount of error given by the amplifier. So sabi natin kanina, this valve may open 20% open, mababang flow rate yon, no? Pag 80% open, mas malakas ang flow rate nun. So, paano ba siya nagva-vary ng 20%, 40%, 60%, or 80% open? Depende yun sa amount ng voltage error na binibigay ni differential amplifier. Okay? So, flow rate is varying here according to the setting here. Okay? While the drain, there is actually a constant outlet water flow rate, no? Sorry about that. What I'm trying to say in the constant is the diameter. There is a fixed diameter, but the flow rate may be varying according to the actual water level, because by the principle of Bernoulli principle, no, in physics, that as the water level is higher, then there would be higher pressure, then there would be uh, greater flow rate. But if the water level is less, so that there would be less pressure, so the flow rate will be less also. But that flow rate, it's still bounded, no? Yung pinaka minimum na uh, at pinaka-maximum rather na flow rate na pwedeng ibigay dito ay still limited sa diameter ng drain pipe na ito. Okay? So once more, the water coming out from the drain, it has a flow rate. So the water is draining, no? This representation, the water is draining, while this representation, the water is filling. So filling minus draining, it will provide what is the output water level being provided here in the bathtub. Okay, so it's also important, that's why in the problem it is stated that you are required to identify what type of signals, no, coming out from each block. Okay, so that you could analyze well the actual flow of the process. Okay, and again, I have here a float. Okay, so the actual water level is being sensed by the float, and that water level is converted by the float into an equivalent electrical signal. I have not drawn here a summing junction like this one, but of course you can draw the summing junction. Kaya lang pinag-isa ko na lang, ano? So the summing junction and the controller amplifying function is as one na sila. As one na dito sa differential amplifier. Okay? So with the block diagram that you have submitted, you have here a potentiometer. No problem with that. That may be also correct. But we will discuss that further in detail, the design of such potentiometer in our next topic, modes of control. We are going to have examples there that we have potentiometer in this portion and potentiometer in this portion. Actually, there would be a bridge circuit, no? Again, the word is bridge circuit, no? So that would be another discussion. But for now, to simplify, so you could relate well, I just represented it by a differential amplifier. Okay, so I hope with this discussion, it is being clarified to you. The block diagram that you have submitted, you have understood, and the equivalent schematic, no? Because most of you have not given the correct schematic, or kumbaga maraming kulang, no? Your block diagram is almost correct, but I didn't able to evaluate if you really understood, because your schematic submitted is somewhat very different, no, or incomplete. Okay, so thank you, and that's all for our discussion in this simplified water level control.